stats. Do this. Oh, I got 2 of them running. Excellent. 3 of them running. That's good. What the heck? What do we got going here? That one's running. Why can you multiply? Okay, stoichiometry and solutions. Nothing magical, nothing crazy about this. This is just regular chemical reaction calculations. Just as we've done in the past. You've got the questions, so I can just start on with this. A strip of copper, the excess reactant, so it's telling us it's excess, was placed in 50 milliliters of 0.5 molar solution of silver nitrate. What mass of silver nitrate was formed in this reaction? First thing we always need, a balanced chemical equation. So again, I'm hoping that we can go ahead. You can go ahead of this without me. I've got copper and I've got silver nitrate. I'll give you the copper. Ooh, copper. Formula for silver nitrate. Ag, NO3, 1,1. That is a successful crossover. This is a single displacement reaction. You could check to see if it goes. If I gave you one that didn't go, it wouldn't be much of a question. There would be no mass. There would be nothing produced. So this will happen. What are my products? Yeah, TJ?
Copper nitrate, which is the
NO3, and its most common oxidation state is 2. All right. Plus Ag. And we need to balance it up. I've got 2 nitrates there. I need 2 silver nitrates there. And 2 silvers there. All right, just like any stoichiometry problem, we get a balanced chemical equation. And again, just like any stoichiometry problem, we're going to write our information under the particular things that we have and what we're looking for. We have 50 milliliters of 0.5 molar solution silver nitrate. So here I've got 50 milliliters. Now, we need to keep in mind that that 0.5 molar stands for moles per liter, and that's the conversion factor. Remember, for molarity, the concentration is the conversion factor, and it has units moles per liter. So if I was to be making my map, right, and I'm heading down this way, right here where I put mm for molar mass, I put my concentration, and because I will always have to be given that number, I'm going to write it down in the map. So I'm going to write this as 0.50, and I'm going to change that to moles per liter. So capital M molarity is the concentration, and it is the conversion factor. We're asked for what mass of silver, ? Grams. And just like any stoichiometry problem, I can go from milliliters now to moles. Actually, I can go from liters now to moles. And then I can go from moles, horizontal line. We know the way that works. Moles to moles. What conversion factor do I move horizontally with? Mole ratio, excellent, very good. And now I can then move up to there. Moles to grams? Oh, the indoctrination is almost complete. Excellent. I feel like Darth Vader. All right, so that one is given. We've got it in the spot it needs to be. Mole ratio we can get from our numbers. Molar mass, we'll just put it aside here. Ag. I'll take it when you find it. TJ, what do you got? 107.9 grams per mole. Pardon the squiggle on the side there. So now we have everything that we need. Now this is moles per liter, which means I should start with liters. But you know what? If I didn't convert that to liters, instead of getting grams at the end, I'd get milligrams, because my liters would cancel out just the liters part of the milliliters. So you could leave it as milliliters. I'll actually do that near the end as an example. For now, let's convert it into liters. So for the conversion, don't forget it's a three-stepper to the left. 1, 2, 3. That's 0.050. And that is liters. And now, if I've made the map correctly, and some of us on our last test kind of got away from the map. If you are struggling with this stuff, make the map, because it's going to guide you on what to use. Because some of us even had the order of the conversion factors kind of randomly mixed up. This tells us, next I'm going to use the molarity, 0.05 moles per liter. I've got liters on the bottom, so I need 1 liter on the bottom and 0.50 moles on the top. Next, it tells me to use the mole ratio. Again, as a review, what I have, and I'm starting with this number, it goes on the bottom, and what I want it to be, that guy goes on the top. In this case, I need a molar mass. And I have moles left. These liters, if I cancel out, I'll use a different color here to cancel out. Liters gone, liters gone. Now I've got moles, and I need moles on the bottom. This is grams per mole, 107.9 grams per 1 mole, and that will leave me with grams. Jess, you got a number? 2.7 to 2 significant digits right there, right? We've got 2 on the, actually, we've got 3 on the volume. Could actually have another 0 on the end. 2 on the concentration, 4 on the mass, 2.7 is good, and that's grams. Yep. Yep. Yeah, if anybody else needs a calculator, I've got some more up here. All right, so I'm hoping that you're thinking, hey, I know what molarity is. That's easy. This should be pretty straightforward, because it should. At this point, it's just practicing doing more of the same. All right? Okay, let's take a look at the next one. 100 milliliters of silver nitrate solution was reacted with excess copper metal. This is the same reaction, right? We've got silver nitrate and copper metal again. 1.8 grams of silver was formed. What was the concentration of the silver nitrate solution? So we have the same reaction, so we'll just quickly get to writing that balanced chemical equation. What do we have? It's copper, and I think we needed 2 silver nitrate, right? 2AgNO3. And we ended up with copper nitrate, CuNO3, 2, and 2 silvers. And again, you know, we're looking at the question. We haven't really thought about what's happening yet. Let's write down the information we have. We have 100 milliliters of silver nitrate. So under silver nitrate in that grams and milliliters section, 100 milliliters. We have 1.8 grams of silver, 1.80 grams. This is looking a little funny. We've got some 2 numbers up here, but let's not worry about it. And the question is asking, what was the concentration of the silver nitrate solution? Now, this is a little different. This is different because concentration is a conversion factor, and concentration usually goes right there underneath our volume when we're given a volume. So in this question, we're actually looking for a conversion factor. Now, we've not done that before, because if I want to find the molar mass as a conversion factor, I go to the periodic table. I just go and get it. So the question might be then, oh, how are we going to do this? We've never solved for a conversion factor before. What I did when I introduced you to molarity was to kind of guide you when you get stuck on something like this. When it asks for a concentration, what did I want you to do? C equals N over V. So we're eventually going to need N and we're going to need V. And what I've asked you to do when finding a concentration is to just use your knowledge to find the V and find the N. And if you can do that, you're going to get the question correct. All we got to do is find those numbers. I also like to put a little C equals N over V, kind of where the conversion factor goes, just to remind us that it is a conversion factor. Well, I don't even have my map completed. I might start to, I might be panicking at this point. Oh no, how am I going to get this? So instead of panicking, I'm going to start looking for those pieces of information. Do I have any of that information available at this point? Yeah. I've got the volume because I'm looking for the concentration of the silver nitrate, and I've got the volume. For concentration, we need it in liters, 0.100 liters. Actually, I got an extra significant digit in there. I've got a fourth, but I didn't put it in. I don't have I could turn that L to a 0, but I'm not going to bother. We'll look at that later. So what's the only other thing I need? Yep, Jess? The moles of silver nitrate. Now, we all know the way our map works. Someone describe to me or even point out on my map, where would I find moles of silver nitrate? On the map, where is moles of silver nitrate located? Pausing for thinking. Letting everyone think. Taylor, what do you got? Right underneath what? Right underneath my little C equals N over V? That's exactly correct. That is moles of silver nitrate. So what we now need to do is we need to mathematically, let me just put it in here. This is our moles of silver nitrate. This is actually the N that we need. How am I going to find that? Can I make a map that's going to get me to that location? I hope so. What are we going to do? Somebody tell me which way to head. And I'm ignoring TJ because I'm wanting some other participation. How am I going to get there? Brett, what am I doing? Okay, where am I heading? And what conversion factor? Yeah, very good. And then what? Yeah, very good. So what we have to do here is we have to do a little kind of partial conversion factor calculation where we stop at moles and then we just put it in. Because we know this relationship exists, we should be able to get it. Excellent. We already have the molar mass for silver, so let's just do the calculation. So according to the map, I got to use the molar mass of silver. What was that, 107.9? With 1 mole on the top. Now I need the mole ratio. I'm starting with silver this time, 2 on the bottom, going back to silver nitrate, 2 on the top. And this is where we kind of got in trouble on our test. We just wanted to put another molar mass right on top of that thing and just, turn it into grams. But we don't need that. We're stopping right at moles. So what is the number of moles we have, Jess? 0, 1, and I've got 3 significant digits here and 4 here, so I want more than 17. 166? 167? 167 moles. Because I've got 3 significant digits there, 4 there. Those are all whole numbers. 0.0167. Don't clear your calculators. 0.0167 moles. If you keep the number in your calculator, all you're doing is dividing by 0.1 equals, TJ? 0.167 moles per liter. And my answer is hiding in the middle here. That's my final answer there, hiding in the middle there. Because I had to do a couple of little calculations there. All right? So we've now done a stoichiometry problem that also allows us to find the concentration of. This is distinctly different than when we first learned about concentration and I gave you a mass and you had to turn it into moles and then just use C equals N over V. This is different because we've now used a chemical reaction to find the moles. but we still use C equals N over V. We don't panic over it. All right, let's do another one. So what volume of 14.8 molar NH3, which is ammonia, would be required to react with 1,000 liters of 12.9 molar phosphoric acid in the formation of ammonium dihydrogen phosphate? All right, so balanced chemical equation always. NH3 plus phosphoric acid. Oh, you guys put your hands down. Let's see if we got someone else. We've got to make sure everybody eventually gets this acid thing. Phosphoric acid. The Callahan girls are whispering loud enough so that everyone in the entire room knows what the formula is at this point. Excellent. Kristen, what do you got? H3PO4 comes from phosphate, which has a -3 charge. We fill it full of H pluses. We get H3PO4. Oops, I want an arrow at this point. Now, this is kind of an interesting reaction. What happens here is one of the H's falls off of the H3PO4, is donated here to the NH3, making it NH4 ammonium, and now we're left with a dihydrogen phosphate because that's what's left after it's given its H away. So that's an H2PO4, and they both have a charge of 1 and -1, and so that's the reaction right there. These two substances, which are molecular, trade one H, and they become an ionic compound. It's kind of neat. Let's write our numbers down underneath like we know how. What volume of NH3? Question mark, liters. And I'm going to put just a line there, no arrows necessarily, because I'm given the concentration. Molarity is always the concentration, that capital M, 14.8 moles per liter. When I write it as a conversion factor, I change the unit to the moles per liter because that's how I'm going to have to use it. This is 1,000 liters, 1,000.0 liters, and its conversion factor is 12.9 moles per liter. I'm starting here and I'm ending there. This is, this isn't a limiting reagent problem or anything. I'm just figuring out how much I need. So that turns to moles. I'm heading over here. That turns to moles. And now I can put an arrowhead on this one and finish the map. So this is just a whole bunch of solution conversion factors. There's no trick to this one. I'm not looking for the concentration. I'm just looking for liters. And again, I just start with what I'm given, 1,000 liters. I follow the map. Again, we did quite well on that last test, but there's a handful of us that are still not sure where to go. The map guides you. I've got liters there, 1 liter on the bottom, 12.9 moles on the top. This is a 1-to-1 ratio, but still, the number I'm starting with, I want to get rid of that. It's got to go on the bottom. For one H3PO4, there will be one NH3 formed. Tells me I need a molarity conversion factor. What goes where? What goes on the top and what goes on the bottom? Brett? 1 liter on the top because I need liters out as my unit, and 14.8 moles on the bottom. Notice how this is different to a molar mass. A molar mass has the one with the mole number, and the other number goes with grams. For a molarity, the one goes with the liter, and the other number goes with moles. So it's kind of, it looks like it's upside down, but it really isn't. It's in the right way, but it's different. And it looks like we've got 3 significant digits as our limiting thing. TJ, what do you got? 872 liters to 3 significant digits. Supporters? Yep, we like it. No trick to that one. There just wasn't any grams in that one. But again, notice, whenever I'm dealing with a solution, if the question isn't asking for concentration, all right, then you will be supplied with all the concentrations. They have to give you that in the question. There's no way to know it by like a molar mass. We just need the identity and figure out what it is. Here, there's no way to know. You've got to be given that information. All right. Number 4, and then as you can see, there's a number 5, and then I'll let you work for the rest of the class here. In an experiment, a 10 milliliter sample of sulfuric acid solution reacts completely with 15.9 milliliters of 0.150 molar KOH. Determine the concentration of the acid solution. Okay. Sulfuric acid. Yeah, H2SO4. And KOH, that's an easy one. Products. Yeah, yes. H2O, K2SO4, and balance. Yep, Taylor? 2 in front of the KOH, but then how many H's have I got here? And how many OH's? So how many waters? Yeah, 2. And let's write the information down. I have 10 milliliters, 10.00 milliliters of the H2SO4, and I have 15.9 milliliters of the KOH, and I also know the conversion factor of the KOH. It comes right with it. 0.150, and that is moles per liter. And it says determine the concentration. What do I write down? Yeah, C equals N over V. And this is moles. And I can get over here to moles. And then what I'm doing here is I'm looking for that C equals N over V. Now, I'm going to do this a little differently, all right? Let me just show you one other thing here off to the side here. C equals N over V. That is our conversion factor for finding molarity. And I can get that by putting the number of moles over the number of liters. And that gets me moles per liter. But I can also get that in another way. I can actually put millimoles over milliliters. If I use millimoles over milliliters, you'll notice that the millis cancel out, and I'll still end up with moles per liter. Now, you don't have to do the questions this way. You could convert everything to liters and everything to moles. But let me show you why this works the way it does. It works really nicely. I'm looking for the concentration of sulfuric acid. And I'm given that sulfuric acid in milliliters, which means that's the V that I already know. And I can easily put in here 10 milliliters. Now, as soon as I do that, it means that my N must be in millimoles in order to get the correct concentration. Notice I'm going to start with my milliliters, and I'm going to head over here to get these moles right here. If I put it in milliliters, it means that in my conversion factor, if I start with 15.9 milliliters, in the end, I'm going to get millimoles. It saves a lot of converting, right? It saves me going from milliliters to liters and back and forth. So you can work in millis. It still gives you the same answer. So if I have 15.9 milliliters. I'm still looking at this liter. I'm still going to use this conversion factor, and I'm going to put it in as 0.150 moles per liter, and that's going to cancel out the liters part of my milliliters. I'm going to use the mole ratio. Again, what I have on the bottom, 2. What I'm looking for on the top, 1. And I'm going to stop right there, and that's going to give me a unit of millimoles. How many millimoles have I got here? TJ? 1.19, and we only need 3 significant digits, right? 1, 2, 3. So that's good enough. You could keep the 2.5, but no, I think we want to stop right there. 1.19. 1.19 millimoles divided by 10 milliliters. What do we have? Yep, Scott. 119, and that now has a unit of moles per liter, which is what we want. And the reason it has a moles per liter is because the milli and the milli cancel out. All right? So I've been telling you, make sure you convert it into liters, but if you don't, it just means you've got millimoles or milligrams, depending on what you're measuring. And if I don't ask you what unit to put it in, then I'm not that concerned. I am concerned, though, if you're asking for a concentration, I do want it in moles per liter, and there's that final answer hiding in the middle because of the way I explained to you how to do it. Okay? All right. If you do not like this working in millis and you want to convert everything into liters, then by all means go ahead. You'll get the same answers. I'm just saying that don't be afraid of the prefixes that we deal with in terms of the metric system. They just represent a power of 10. It's not a big deal. All right. Last one. Oh, one last little thing. Let me just go back to this guy. Oh, can I? Yeah. This is not too tough of a problem. We got a balanced chemical equation, and we're going to, figure out a concentration. But what some students will do when they get stuck on this, you'll notice when you look at this question, it says, oh, that was horrendous, 10 milliliters and 15 milliliters and a concentration, and it says determine a concentration. And what students will do when they get stuck is they'll say, oh, I've got an equation that has concentration and volumes in it. I've got C1V1 equals C2V2. And I'm missing just one concentration. Why don't I just stick it in that equation and get the answer? When do we use this equation? What is this equation used for? Yep. Dilutions. This is used for dilutions. I would write dilutions, but I'd spell it wrong. So I'm not going to. But that's only used for diluting something. That doesn't involve a chemical reaction. And you wouldn't get the right answer for this one because it's a 2-to-1 ratio. But I know that some students, sometimes I give them a reaction that's a 1-to-1 ratio, and this equation actually gives the correct answer. But it gives it for the wrong reason. If you were to use this equation in the wrong situation and get the right answer, I'm not giving you full marks. I'm likely giving you a token 1 for I don't know, so that you don't come and complain to me. But I got the right answer for completely wrong reasons. So this is dilution. In a dilution question, it'll speak nothing of a chemical reaction. It'll say, I have this solution and so many milliliters, and what's the new concentration if I add, if I dilute it to, right? It won't talk about a chemical reaction. So don't use that equation in a stoichiometry problem. Okay, last one. 15 milliliters, 0.7 molar sodium hydroxide, reacted with 15 milliliters, 0.85 molar aluminum nitrate. What mass of the precipitate is formed? So we got lots of information. First thing, of course, we need is the balanced chemical equation. Oh, I don't like red. Sodium hydroxide. Formula for aluminum nitrate. Yep, Sean. Nope. Yep, Scott. Yep. 3 and 1. Aluminum is 3, nitrate is 1. Products. Yeah, TJ, what do you got? ALOH, and we need 3 of those. The question asks, what is the mass of the precipitate formed? Now, even though we're talking about a double displacement reaction to form a precipitate, I don't need to see all the little AQs. You know, when I ask you to do that in the double displacement reactions, like on an exam, if I ask you to do that and there's no stoichiometry involved and it's just a double displacement reaction, then yeah, show me the AQs. But if I'm doing a stoichiometry problem, I only want it for the mole ratio, really. But you do need to know what the solid is in order to identify that mass. Which one of these products are going to be solid? What's that? The aluminum hydroxide. Why isn't the sodium nitrate solid? Yeah, it's got sodium and it's got nitrate, and they're all the ways aqueous. So you can check aluminum hydroxide. You'll see that it's got a little solid. I'm going to put a little solid right there, just because that's what it is. But you could also indicate it with a question mark grams, right? How many grams are we looking for? So let's balance this one up. I got 3 nitrates, so I need 3 of those, and I got 3 hydroxides, so I need 3 of those, and I think that takes care of it. And now again, the rest of my information. 15 milliliters. Concentration, 0.75 moles per liter. And this is 15 milliliters. And this is 0.85 moles per liter. And you'll notice I've got information about both of the reactants. What do I have to do? Just pick one and just go? No, we don't just pick one and go. What do we call this problem? It's a limiting reagent or a limiting reaction problem. We got to figure out which one we have to use. So we need to convert this into aluminum nitrate needed. So I need to figure out moles. I need to head over here to moles, and then I have to eventually figure out how many milliliters I need. Now, you could convert this into liters, but then you'd have to convert it into liters to compare it. If we keep milliliters here, our milli is going to carry to the other side, and we're going to get milliliters on the other side. So we can keep that as milliliters. 15 milliliters of sodium hydroxide. I'm going to use its conversion factor, 1 liter on the bottom, 0.75 moles on the top. The liters, cancel away the liters. I now have millimoles, but that's okay. I'm not really that concerned. Just keep going. Mole ratio, 3 to 1. Now I need my liters back out. 1 liter, 0.85 moles on the bottom. And again, notice, now the moles are gone, and the unit I'm left with is the little milli that I had at the beginning, and the liters that I have right there. That's going to give me milliliters. That's handy because I got to compare it to milliliters anyway. TJ, what do you got? 4.4 to 2 significant digits. As I've said in the past, always go back to what you have. Oh, you know what I forgot to do? I forgot to write down ALNO33 needed. And that's a little step that you should write down. That you really need to get into your head. That's what I need, and 15 milliliters is what I have. So I bring my eyes back to the 15, and then I head down this way. I have 15, but I only need 4. What is the aluminum nitrate? It's excess. So therefore, it is excess, which means this is the limiting reagent, and we use this guy. Okay? If I use 15 milliliters as my starting number, what's my mass going to be in at the end? Yeah, it'll be in milligrams. Well, the question doesn't specify what unit to state the number in, so there's nothing wrong with that. By the way, my new map, I'll use a different color, starts with the limiting reagent, works its way all the way across here. Moles up to here. Oh, what do I need here? Yeah, I need a molar mass. Maybe I should do that. ALOH3. Well, by the way, folks, it seems that when we deal with some of these ions that are in the brackets, we forget to multiply the inside letter by 3 as well. Here's a neat little trick, especially for something like hydroxide. We know that oxygen is 16 and hydrogen is 1, so you could just do a 17 times 3, right? Hydroxide will have a mass of 17. Now, with something like nitrate, that's not as nice because you've got nitrogen and 3 oxygens. But you've got to remember to multiply that in for all of those atoms in the brackets. Look at what I just did. I just did AgOH, and it's Al. That's from the previous questions. What's aluminum? 27? And these are all 0.0, so we're going to get something 0.0. 78? 78.0 grams per mole. Scribbling the moles again. And now we just fill in our stuff. Follow the map. I'm at this 15 right here. 0.75 moles per 1 liter. Mole ratio. Number that we have on the bottom. What we want it to become, 1 on the top. This is now a molar mass. Again, I've got to get rid of the moles, and I want mass, so the 78 is on the top, and the 1 mole is on the bottom. So be aware, molarity is a little different of a unit. It's so many moles per liter, where a molar mass is so many grams per mole. So you got to deal with them a little differently. So we got a number? TJ, you got a number? 878? 870. Whoops, what am I putting a decimal in there for you? Oh, we don't like it. Good thing I'm making a mess of it. We'll get rid of it. What do you got? 0.29, and 2 significant digits is good, grams, which means this is going to be 290. 292 milligrams, and we've got 2 significant digits right there, so that would round that to 290 milligrams, okay? If you dislike this milli business, you don't have to do this. You don't have to deal with it. You can convert it if you want, whatever is more comfortable to you. What I'm saying here is don't be afraid of it, though. It's something that can be worked in the whole system if we need to. All right. So that is our little kind of review of stoichiometry. So there are some questions there that deal with this out of the textbook. Those are the answers to that little sheet I gave you. So you could write them down, or you could even write it right on the sheet if you'd like. And then I do have one more slide, which then contains our review problems that you can work on tomorrow. And if you're not here, obviously you can work on them as you're in between events. For track star. Before I give you the review homework, I just want to point out one question on this page that really messes people up, and that is number 2. All right? And if you just take a look at number 2, it says an iron nail is placed in a test tube containing copper 2 sulfate. Most people, when they do that single displacement reaction, they want to use iron 3 sulfate because the oxidation state 3 for iron is in bold, and I've told you, use the bold one when there's a question. But in this question, take a look at part B. It says, what's the mass of iron 2 sulfate formed? And so in this question, we're asking you to use iron 2 sulfate instead of iron 3 sulfate. If you use iron 3, your numbers are off because your balancing is off and your molar masses are slightly off. So in number 2, we're asking you to use iron 2 sulfate. That's just, I didn't write these questions. Whoever wrote it asked, decided for that. But it messes everybody up because they always just do it without thinking, which is good. We want you to think that way. But just letting you know so that you don't struggle with why you've got the wrong answer.